All right, folks, let's get started. Well, I can't really tell on Zoom, but at least the people in the class right now don't seem to be hating each other. They actually seem to be talking amongst themselves before class started. So hopefully a good sign that friendships are being repaired and all the scamming that went on is being forgiven. Oh, you're a bad scammer then. Probably could have got way more people scammed. Yeah, so we'll grade that assignment very soon. I'll share the results. I'll try to have that done by Thursday. It's always interesting to see the distribution of things. Let's see, some of the scams. Actually, what I'm super interested in is knowing about ways to scam people that I don't know about because I've been doing this for a decent amount of time. One of the things is, so how do you tell that a key is the same key in GPG?
Fingerprint.
The fingerprint. What is the fingerprint?
Fingerprint is a alphanumeric.
Yeah, what is it? How is it generated? Why can you trust it?
It's a checksum.
Not a checksum. If it's a checksum, you definitely can't trust it. Similar to a checksum. You just trust something, you don't even know what it is. Could be random letters.
It's a fingerprint.
Yeah, fingerprint. How's it created? What was that?
Was the fingerprint?
Nope. It's a GBG thing. It's not something I did.
We're asking the algorithm that's used to generate it. Make sure that's a unique algorithm.
Yeah, what have you learned about to tell when the integrity of something has been violated or changed in a cryptographic way? Hashing, hash functions? No. Very different. Checksums are not cryptographically secure and they can be easily broken. But yeah, so the fingerprint is a cryptographic hash. I don't know exactly what algorithm it's using of your public-private key. That's why the only public key that you should trust has this exact fingerprint. And actually, one of the big design flaws of GPG is that it will show you different fingerprints. So sometimes in the output, it will just show the last, I don't know, 8 or so digits of the key. This is also known as your key ID, is the last part there. But the whole thing is the fingerprint. And so that's what you need to download, or that's what you need to check to see, is this key that I'm signing actually signed by the real core signature? What's preventing anyone else from creating a key with the name CSE 365 Spring S22? Nothing. So yeah, one of a very cool way that people scam people is you get your adversarial key. What happens if you edit the name on a key? The signatures go away. Why do the signatures go away? Yeah, the keys changed. It's not that it's considered a new key. Everyone who signed your key to verify your identity was verifying the name and email address that was on your key at that moment. When you change that, you lose those signatures. But the key still remains the same because it has the same fingerprint. Yeah.
So you create an average serial key, you're telling me that you actually edit the name?
Correct.
You generate it?
Yes, but then what happens to that key?
The signatures?
The signatures go away, including the course signature.
Well, but I mean, I guess you get the course signature, but I figured if you don't have any signatures on that serial key, it wouldn't really matter, right?
But you shouldn't sign a key that's not valid, right? And only keys that are valid are signed by this hash, like this fingerprint of this course key, right? So before signing a key, if you always validate that it has a signature by this and you validate the identity, those are the two big steps.
I was just thinking like, if you want to discount people changing.
Yeah, so if you're scamming people, you can change the adversarial, you can change the name to your name, right? Back to your name. It drops the course signature, so it's no longer signed by this. So how do clever attackers get around that? make your own course signature key. So you create a fake CSE 365 Spring 22 key, you sign your own key, but now if you send that new adversarial key that has this fake course signature, if you just sent that to somebody, what would they see when they list the signatures on that key? They would see user ID not found. So that would be a clear indication that that signature is not valid. So how do you get around that? Yeah, you can export both of them to one file because GPG, when you import keys, will import everything that it sees as a possible key. So you send people in one file 2 keys, your changed adversarial key and your
false CSE key.
Your fake CSE 365 Spring 22 key. And then when they do list SIGs, they see, oh, it's signed by CSE Spring S22, but the fingerprint will not match. Yeah.
I was only checking the I1E at the end. Is it someone plus potentially made something that is when that I1E?
Yeah, you could continue to generate adversarial keys until you had one that the fingerprint matched enough of the digits that they maybe wouldn't tell. I don't know I can't remember exactly how much of the key ID it's used and how much you need to try to generate in order to get something that matches exactly.
But I figure it'd be very time.
Well, if you run a script to do it, you don't have to do it yourself, right? You write a program to do it. Yeah, Zoom chat is saying when you import keys, so if you're very careful, if you're importing keys, it would tell you, oh, hey, your import, like, I imported 2 keys. So if you're looking at that, you can spot this, this type of scam.
And of course, you automated things, in which case you may get tricked.
You most probably did, unless you had safeguards in place.
Yeah.
Cool. Well, any other scam ways that people either came up with, or you could say your friend came up with, if you don't want to admit to scamming people yet?
I use the ASU chat. Sorry.
Oh, it's okay. Go ahead.
I use the there was this thing on the ASU app. I just found people there. Then and I just did my best to just see if the email and the name matched.
So that's you're talking about how you verified that the key was correct.
Yeah.
Yeah, I'm interested in how people scam people.
That I made sure that was the closest I could think of to make sure I wasn't signing in an adversarial key.
Cool. Thanks. You had your hand up.
So one thing that I did see is someone changed their adversarial key to their roommate's name and email. So when you try to verify their email, they just use their roommate's.
Yeah, I've seen that before. Yeah, one student, or I've seen that in the past where people got permission from other students in ASU to impersonate them, even though they're not actually in the course. So you would see that they're a real ASU student, but not the same person. But you still have the same problem with changing the name, right? With the you'd still lose the fingerprint and those kinds of things.
Yeah.
Oh yeah, so that's Zoom chat is saying that a few people just playing like you don't know what you're doing, so pretending like you don't know what you're doing. And so if they ask you why isn't your key signed by Gradescope, you just say like, oh, I don't know, like I didn't even know you were supposed to do that part of the assignment. And so if you can convince the other person that you don't know what's going on enough, maybe you can scam them. Yeah.
I had a couple. I guess the first one is starting off by creating a generic email.
Okay, so creating a generic email from the start, so it wouldn't be tied with like your ASU handle and ID.
Yeah, because one thing I noticed is kind of like what somebody was saying in the chat is most people had to have their using their ASU right email, so it's like it's the last one.
Yeah, right. So the only requirements on the assignment was that the name matched, right? We said nothing about the email and nothing about that. So if you waited a little bit and maybe asked around people, you could see what their names and emails were. Cool.
I guess just finding people who didn't know what they were doing.
Yeah. Anybody wait till the last day to scam people?
Yeah.
I bet it was a bloodbath. It usually is. That last day is just like wolves coming in and getting a bunch of signatures on their keys for sharks. I don't know however you want to think about that. which also parallels real scammers and real cybercrime, right? They take advantage of people's their fear that they're getting audited by the IRS. They take advantage of the fact that they're under a stressful situation in their job to try to get them to trick them to do something. So you can take advantage of people in those kinds of situations. Anybody have what they think was a really good defense? Like did anybody like meet in person and only do key? Yeah, go ahead. Louder.
So this is something a friend told me, but I forgot what it's called. There's like SC for like a lot of keys, and I think most people like regular keys have like SC, but like all the adversarial keys have SCEA. So if it had SCEA, unless the person knew how to like change that for their public key, that's like almost like it was almost guaranteed that was the case, or at least I just made sure not to sign key.
Yeah, that's probably an artifact of honestly the different versions of GPG that's running on the server that's generating the keys. So it's using a different version of GP, like an older version, because it's the only one that you get running. Anyways, it's a very long story, but the point is you're basically trying to highlight differences that exist. But how did you find that out? Did you share adversarial keys with people?
No, it was more so just like I was talking to a friend that he like told me, and then when I looked at like my own adversarial key, I was like, oh, there is a difference.
Nice. So some cool like proof of truth that I've seen is people only like always sharing their adversarial and their real key to somebody. So whenever you wanted to sign, you had to show like, here's my real key, here's my adversarial key. Don't sign the adversarial one, only sign the real one. And that's why how you know you can trust me is because I'm giving you and telling you my adversarial key. Yeah, so in Zoom chat talking about figuring out someone you trust and then using like comparing fake adversarial keys that way. Yeah.
I don't know if it's mentioned that one closely, but the iSearch function.
Mm-hmm.
And it seemed that they matched the name of, you know, I know they were your science degree.
Cool. So using kind of, we call it like OSINT, so like open source intelligence, right? So all the information you could possibly find out online to see if they're a real person or not. Did anybody do anything sketchy with the Discord? I was thinking it would be really funny to like create fake Discord accounts and join a Discord. One year before, I think it was when we were only using Piazza and we weren't really using Discord, students created their own fake Discord server for the class, got people to join for key signing, and like 10 of them would just like they had how to do the assignment, but it was all wrong of like how to check keys, and they would just everybody that joined that Discord would get their like they would sign 10 people's adversarial keys like every time. Yeah, screenshots. So people asking each other for screenshots of your like ASU ID card. Anybody fake those? Or want to admit to maybe faking them? Prepared to fake it, but didn't actually use it. Yeah, you can fake that. You can fake screenshots, right? You can take a screenshot of your My ASU. You can change anything in there. Yeah, so there was a Discord that existed where there was only legit people. I would be shocked if everyone on there was legit and nobody scammed anyone. Yeah.
Okay, so I actually started that server, the same key server,
Uh-huh.
but it kind of like evolved. It's funny how like it all started like everyone really like share safe keys,
Mm-hmm.
do the right thing. As time went on, they made like a server.
Like a new safe server. And yeah. One year I did this, the students asked me before class if they could like stand up and announce something. And I was like, sure. So they stood up and announced that they were going to create their own certificate authority and they were going to verify everyone's identities to get on a Google Doc. And that way everyone who had, you know, name, email, key ID, everything was valid on that Google Doc. And somebody infiltrated their group and like scammed their way on. So they got signatures from all of those people on their adversarial key. So trust is really difficult. Okay, that's weird. They found out somebody went to their old elementary school, so looked up their yearbook from elementary school to see that they were a real person. That's pretty in-depth. Any other good scamming or defense stories? Yeah.
Like a foolproofly, but like it's sort of like just another layer of like. So when I started like getting signatures, it was like about the midway point. So that means most people who want to advocate for signatures have that like a decent amount of signatures on their key. So for adversarial keys, unless you're really good at scamming, and like as long as you have like a bunch of other students are your key rings into one like a midway point. If you notice like, okay, this guy has like his share of like 10 out of my 15 keys, it's like, unless this guy's like a god scammer, it's probably
That's
not that.
That's pretty funny. Yeah, so that kind of means you'd only likely to get scammed by people who are really good scammers, but there's probably a very few of those anyways. So maybe that's actually a good like defensive technique.
I mean, I get no offense to people in class, but I feel like that's what people just want.
You'd be surprised. Or any of the undergrad TAs in here who did the class with me last year. I think the lead scammer there. Yeah, do you remember what Prime Danny got? Was it 110, 120? Over 200. Yeah, it was great. That was last year. So I'm super excited to dig into the results here and see what happens. So I was also completely online class and all COVID. So I have no idea if maybe being in person has a positive effect in your ability to not get scammed. So anyways, it'll be super interesting to learn. I'll as a heads up, I'll probably just reach out to the person who was the best and see if they'd like to talk for 5 minutes or so about their techniques. Of course, they don't have to, but it's always cool to see how they go about that. Anybody do more than 200? Of course, I still won't trust anything you say until I verify it myself, so that's okay. But just wanted to see if anybody, yeah. 300 would be insane. We'll have to, maybe I'll have to keep like a leaderboard. I'll have to adjust it based on how many students were in class, like what population of the class. All right, and on that note, cool. And okay, before we jump onto back to network security, we will be having our midterm CTF starting tomorrow. I don't know what exact time, so we'll announce it soon. But it will be a week-long CTF, just like the other types of things. It's going to be on the pwn.CSE365.io system. So you'll know exactly when you solve levels, and the challenges will all be based on stuff that we've been doing previously. So it's an application of your crypto, your networking, your access control, all that kind of stuff. So should be good. Cool. All right. So before we all left for break and then devolved into horrible scammy people, we were learning about networking. So somebody remind me, what is the process like when I am what's the process like when I want to send an IP packet to another system and we're on the same network? So what do I know? So if I'm, let's see, if I'm 121 and I want to talk to .14, so what do I know? I know what network I'm in. So I know the subnet, mask, I know CIDR, whichever way. I know how to tell if that IP is in my local network or not a local network. So I can use that. I can see Okay, so I know the network. What else do I know? I know my own IP address and I know my own MAC address. What else? I know the IP address of who I need to talk to. And that's it. Right? Those are the only, was it 4 pieces of information? Network info, my IP address, my MAC address, their IP address. That's all you need. Then what happens? So I have all that information. I then use, so the first step is I use the subnet to determine, is this a local net, is it a local IP address or not? I determine, yes, it is a local IP address. Yeah. Yeah, I broadcast because what's the problem I'm trying to solve? Not quite. There's no integrity or ID verification at all. But I'm missing one important piece of information that I can't send the packet directly to this person on my network. Yeah, the destination MAC address, right? Because I need that in order to create an Ethernet packet, which is going to go out on the network and get delivered to .14 if it's available. So that's my broadcast, and I say, hey, who has, so I use ARP, address resolution protocol, and I ask the entire network, hey, who has the IP address 111.10.2014? It goes to all the hosts. The host that is 111.10.2014 responds to me and says, I'm that host, and I'm at MAC address 0A1233B2C411. Sends that back. And then at that point, now the host can send an IP packet. So, which is then layered in an Ethernet frame. Cool. Now we're going to tackle the problem of going back to that very first step, right? Is this IP address on my local network or not? If I say not, it is not on my local network. Now I need to do indirect delivery. So you can think about this, it's very like direct delivery. You can just deliver it directly to that computer in your local Ethernet. Indirect delivery, it needs to go somewhere else. Now it's kind of a question. So if it's not going to any computer on my local network, where does it go? So if we start back at what we know our subnet, we know our IP address, we know our MAC address, we know the destination IP address. Do we have enough information to know where that packet goes? Yeah, so on Zoom chat, they're saying, no, it's like mail. If it's in your neighborhood, you can just give it to your neighbor. But if not, I have to go to the post office, right? So I actually need some other bit of information. I need to know, not just a bit, but I need to know information about where is the post office? Where do I give it to some entity who must be in my local network, who knows how to get that packet somewhere else? And so this is usually called the gateway. So this is why if you've looked at networking, usually what you'll see is your IP address, your subnet, your MAC address, and also the gateway. So basically, what machine do I send this to? So it's another piece of network configuration, and then it's the gateway's job. At this point, we've done our job. We've sent it one hop away. Hopefully that gateway knows where to go. And it basically decides what to do with this. You can think of gateway, you can think of router. So in most networks, your gateway will be your router. So this is the device that you pass the packet to. Your router probably has a connection to your cable modem or whatever. So it knows to send the packet to that cable modem. It sends it to that cable modem. That sends it to your service provider, and then it just keeps going. The important thing is every step along the way is just direct delivery. And this is why this is actually very simple, because we've already studied direct delivery. So basically we have something like, There's me. I'm just going to draw the switch like an X. Well, you need to be able to see it. What's going on? Thanks. Oh, I should just keep that. Okay. So we have me connected to the switch, which is connected to the gateway. So if the gateway is not connected to anything else, where will that packet go? Yeah, drop it nowhere. Like there's nowhere for it to go. So fundamentally, what defines a gateway is that it's connected between, it has at least two network interfaces, and it's connected somewhere else to something on the other end. I'm running out of room and thing. We'll call this G prime for now. That's probably a terrible name. But all of this that is done is all done at local delivery. So let's walk through a scenario so we can kind of understand exactly how this plays out. So A, I'm going to say 192.168.0.2. We're going to say my MAC address of A is, actually, I'm just going to use MAC A. I think that's going to be way simpler. So we'll do IP A, MAC A, IP G. And I'm already regretting using G prime here. So let's just change this to H. Technically doesn't make sense, but sure. I was also thinking that as well. All right, so the IPG is 192.168.0.1 and has the MAC address of G. And let's just take it through this first step. So let's say that A wants to send IP packet to 8.8.8.8. Okay, but I don't have enough information here, right? Because I also need to know for A, what's the gateway 192.168.0.1 and the net mask. So I'm just going to call this a /24. So I can say that, okay, so what's the algorithm here? What does A do? So A wants to send an IP packet to 8.8.8.8. Yeah, is 8.8.8 local to IPA? Well, I'd say to A, including the network. No, right? We've gone over this. No, it's not local. It's not on. It doesn't have the prefix 192.168.0. So it's not local. Great. So now I need to send it to gateway. At some point, the gateway is checked to make sure it's on the local network as well, because if it's not, you can't get any data there. But it obviously is. So is 192.168.0.1 local to A? Yes. So now we need to do local delivery. What's the first step? Yeah, ARP request, basically who has 192.168.0.1, tell 192.168.0.2, right? So that'll send a broadcast packet. Does that packet get to H? No, because it only goes inside this local network here. So it only goes to all 192.168.0 hosts. They all get that. G responds, hey, I have 192.168.0.1 and my MAC address is the MAC address of G. Now, what's the IP packet that host A will send? So what's the source IP? Yeah, the IP of A, which is 192.168.0.2. What's the IP destination? 8.8.8.8. How come it's not 192.168.0.2? Because that's not where this packet is meant to be going. It's just the first hop along the chain. Cool. So we'll also have some like IP data and probably a bunch of other stuff in here, but we don't have to worry about what's actually in there. So we have this beautiful little packet, and that's encapsulated inside an Ethernet. So what's the MAC source of this? MAC A. And what's the MAC dest? Yeah, MAC G. Awesome. Right, so this gets sent out as an Ethernet frame. The switch, we already know how it figures out where to send it. We go back to our diagram. This packet comes from A, gets sent out. Oops, I don't like that. Gets sent out, goes to G. G gets it and says, is this packet meant for me? Yes, it has the correct MAC address. Is the IP packet meant for me? No. So then G has to figure out, okay, and it may have multiple networks. So it has to use, we're not going to get into how that stuff works, but it then has to figure out, okay, how do I get of all my networks, which one gets me the closest to 8.8.8.8? Right? Let's say this network actually, well, let's not do that, but so this will go through many such hops. So, oops, that's super ugly. So let's say G, that packet, then G, then which part of this whole packet remains? So on the hop from like G to H. Just the IP packet, right? The Ethernet gets completely destroyed and recreated because the Ethernet is only used to send it one hop, right? So Ethernet containing the IP packet from A to G, and then the IP packet mostly changes, mostly stays the same. The only thing that actually changes is the time to live value, which we talked about to prevent infinite packets circulating around. So it gets decremented and will get dropped. And then G does the exact same process. So G says, okay, who does this packet need to go to? Am I on the same network as 8.8.8.8? If no, then what gateway do I have? Where am I supposed to send data? And so it would say H, and it would say, great, I need to figure out the, I know the IP address of H because that's my gateway. How do I get its MAC address? I do an ARP request, which never makes it to A, right? That ARP request will only be local inside this network. Sends that ARP request, gets the MAC address of H, then sends an Ethernet packet from G to H. And then H goes on until finally that packet gets to wherever 8.8.8.8's local network is. And then that packet gets sent directly to them. They go, yay, I got a little message, awesome. And then they decide based on that message whether they want to respond, and the process works in reverse. Yeah.
So I'm doing trace route, it gets to one hot place and then it has to send something all the way back every time.
Yes. So to make debugging easier, so this situation is actually basically insane, right? Because you're sending this packet out. You may know that it got to G, but you don't know if G is able to get it anywhere else. You don't know if anywhere else is able to get it anywhere else. So there's ICMP is the is an IP layer message that is used one of the ways. So ping is one of these things. So you can ping something, it's supposed to send you something back with an ICMP message. When a packet is dropped, the machine may, depending on how it's configured, tell you. So it may send an IP packet back. So that's when you'll see sometimes if you are trying to do something and it says you got like gateway says can't connect to host, or I don't know, host says network is down. That means like your router can't get the data anywhere else. So even though you're connected to your router, there's nowhere else for the packets to go. So traceroute works. One of the other ways that people on the path will send you messages. Let's just look at this real quick. So the way traceroute works is it relies on the TTL. So the packet time to live it first sends out one packet with a time to live of 1. So on that first hop, that's decremented, and that router drops the packet. And then if it's configured correctly, will send us back a, oh, there we go. So depending on how it's configured, so I'm getting a packet back from 10.153.0.1, and then these stars mean it times out. So I'm sending this packet and I'm not getting any reply. This is because machines can be configured to not let people know when they're when they've lost a packet. And I guess we'll come back here. But you can use this sometimes to map a network, so you can see all the hops between you and another system. Okay. Cool. So now you actually have all of the fundamental knowledge to understand how data gets from one machine to the next. Now, the question of, again, like we talked about, where does a gateway decide where to send the packet? For your router at home, it's a very simple process because there's only one place it could possibly go. For a company like I don't know, Cox or CenturyLink or somebody like that, they may have many different ways for that packet to go. So how do they decide? But like the shortest route, if you were in charge, what would you do? Shortest route? That way, like the least number of hops. So if I know that you're trying to get to Netflix, like I know based on IP address what ISP Netflix is connected to. So I would send you either directly there or send you to somebody else that's connected there, right? Shortest number of hops. Is the shortest number of hops always the fastest route? Say it again. Yeah, the crazy thing about networking is you always have to think of congestion, right? The shortest path may actually not be the fastest because it could be so congested that packets get dropped and bad things happen. It could be that maybe it's a more direct hop. So you're at one ISP and you're sending it to another ISP that's technically only one hop away from your destination, but you know that their stuff sucks and is really slow. And so it actually could be faster going another way. What could be some other reasons? Is there any non-technical reasons? What drives most decision makings in companies? Money, money. I could have a deal with one networking provider than another. So it may be cheaper for me to send traffic to Netflix through somebody else, even though it's slower and worse for my customers, because they're paying me less money. I have to pay less money for it. And actually the way that networking kind of does really work that's crazy is companies like Netflix, the ISPs pay so much in bandwidth that the Netflix will come to them and say, hey, what if we put a server in your network? That way your customers wouldn't have to talk to anybody else. They could just get content directly from our systems that are inside your networks. And that's like content distribution networks, these kinds of things have all of these arrangements with a bunch of internet service providers. Anyways, the short version is what happens in this networking decisions is insanely complicated due to financial decisions, all kinds of stuff. And so trying to predict what happens is almost impossible. So, but anyways, we actually don't need to worry about that. If you want to go super in depth in that, you can take a networking course, you can learn. There's also the question that should be in your mind a little bit of, okay, but how does my ISP know essentially where 8.8.8.8 is located? Like, how does it even get closer? So there's this protocol, BGP, this border gateway protocol, but it's how networks talk to each other to say, hey, I support these IP address ranges. So if you have any traffic for those, send them to me. and it's how they communicate. But anyways, but we can still completely understand exactly how a packet gets from one location to the other. So remember important things, source and destination IP addresses remain the same along every single hop. The TTL field is decremented at every hop. And the link layer completely changes at every hop, right? Because the link layer, that Ethernet frame, gets completely destroyed because the link layer is only to get it for one hop. And so you're going hop, 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 hop. And the only thing that decides the process of where the packet goes is the delivery IP address, right? Because we're trying to get that packet to where it needs to go. So if in this example, we wanted to send something from 111, 10, 20, 121 to 128, 111, 41, 10, we would need to have that packet would travel through many different switches and gateways, each switch and gateway having its own little network until finally it gets to our destination, in which case the process reverses and it has to go backwards. And at any stage in this process, it uses ARP to figure out where the packet's going and all that fun stuff. Cool. Questions about this? Yeah, it's pretty easy. This stuff's all knowable. Nothing's magic. It's all understandable. I mean, it's way more complicated of what's going on, but the mechanisms of how it's getting from one place to the other is definitely knowable. And you can spend your whole career studying and optimizing these things and studying congestion and what happens if packets get dropped and all this kind of stuff. Like, there's a lot of fascinating things to learn and study in here. But for our purposes, we're just covering how things actually work. So the important things to remember are the various types. Oh, so very funny. It used to be that the delivery route, so the route that packets would take, were determined. So the main way that, actually I think the only way now, is every gateway just decides where the packet goes next. It used to be, there was a back when the internet was more trusting, if you actually were creating an IP packet, you could suggest, hey, you should take these steps to get to your destination. This actually is a horrible idea. It provides a lot of power into the hands of the attacker, because I can now influence exactly where my packets go. I can overload certain links in the network and do all kinds of bad things. And let's see, oh, this isn't very interesting at all. Thanks, ASU. Anyways, so this, we could see a couple machines here. So this 172, 29, 117 was somewhere along here. We could do, oh, it's gonna be the same. Let's see if this works better. Well, it's running on Amazon servers, so I have absolutely no idea if we'll get. Oh, way better. Well, at least something. Yeah. So we can kind of see the path that our packets are taking inside the Amazon network. At some point, it's transitioning from Amazon to something else. Yeah. Oh, again? All right. Sorry. Here was the, here's the ASU one. I think, anyways, something is different. But anyways, yeah, so this was the ASU one that just had a few hops here that you can see this thing, and then somehow it gets to Google. This is the from Amazon system. So we don't actually have any nice names, but we can actually see there's a lot of different hops on the way between us and them. So you can think of this as kind of crazy, like at least even from where I am right now, there's 13 hops to get from me to Google's DNS servers. Like that's kind of crazy, just along the way from us inside here. So one hop would be definitely the Wi-Fi router that I'm connecting to. That goes somewhere else, somewhere else, somewhere else, and it just keeps going until it gets to Google. All right. All right, good lesson. Cool. If you want to get really heavily into this, and you can actually configure all of these things. So you can, you know, most people think of like their Wi-Fi router, like the router is the switch and the gateway, but you can separate those things. You can have a gateway just be a separate machine that has multiple network cards, and you can configure everything however you want. So you can look on Linux, the route-n command will tell you the routes. So it would say, and basically, yeah, it's saying like the way to read this is it's like a hierarchical table, and it basically says, hey, if you want to talk directly to 192.168.1.24, then you need to use ETH0, which is an Ethernet adapter. And if your destination doesn't match any of these prefixes, right? So 192.168.1.0, there's no gateway, send it directly on ETH0. But if it doesn't match, and then 127.0.0.0, so this was the local host. So it's mostly 127.0.0.1, but it's actually a range that's a /8, and send that on the local interface. So that's just goes to your local machine, doesn't go anywhere. And then if it doesn't match any of these, then if it's not any of these addresses, then send it to 192.168.1.1. So you can have crazy rules that say like, if a packet is destined for 8.8.8.8, send it to 192.168.1.10. Otherwise, send everything else to 192.168.1.1. So you can set up crazy complex networking rules. You can also do, we're not going to get into it, but as should be either a little puzzling or you've been dealing with it so long it's obvious, it's that the fact that I'm sending IP packets. I think I have to show both of you. Zoom people, can you see my, you can see the, what did I just type into the thing? You see the presenter view, but not the other thing. Yeah, okay, that's what I thought. All right. What was I talking about? Oh, anyways. So all that I'm showing right now is my IP address. So 172.172.31.18.21 on this screen. I think that's anyways, let me just show ifconfig 0. Okay, and of course I'm gonna have to stop this displays. Okay, now everyone can see everything. There's much rejoicing. Okay, so this network, I'm on the 10.153.177. This is where I'm at right now in this room at this point in time. We can see the net mask is a lot of ones. I don't know exactly how many because it's not an even number with this C. But I'm sending packets from what should be a private IP address. So this 10, I think 10.0.0.0/8. So everything that starts with 10 is a local network address and is guaranteed not to be globally routable. So how in the world can I send packets to Google? Or the reverse side, how can they send packets back to me? So if we go by our simplified diagram, right? So just like in this example, I 192.168.0.2, right? That's another local address. So Google would get that and be like, I'm going to drop this because this isn't routable. I can't actually get traffic there. So yeah, the trick is there's some trickery going on where one of these machines, one of these switches or gateways along the way is actually translating the local network address, changing it with its external network address, and then remembers what it had sent so it can change it when it comes back, when that response comes back. And that's why. If you go to something like IP Chicken to see what your IP address, so the world thinks my IP address is 129.219.8.178. But if I go back here and I did IF, what was this? It was 129. Yeah, I won't see that anywhere. Nothing. My machine has absolutely no idea about this IP address. And yet that's the world. Everything that the world knows about is that IP address. And that's because something is translating my IP addresses. So in your home, when you're on your home Wi-Fi, your Wi-Fi router actually does this automatically for you. So it's translating your IP address. And this is why we haven't completely run out of IPv4 addresses, because not every machine and every network needs a globally routable IP address. Because when you plug into a local network, you can have 10 or 100 or thousands of devices all connected to one gateway that's doing a network address translation. And externally, you only appear as one IP address. Anyways, we're not going to go into how this stuff works, but I did want to just say that to kind of clarify things. Cool. Okay, so yeah, so the routing process, kind of as we've seen this, is we first want to, we're searching, hey, does anything match exactly? Otherwise, search for a default entry. If we can't find anything, then we send a host unreachable or network unreachable ICMP message. So this is what we've seen before that gets sent back. And you can, like I said, you can completely statically create routing tables. This can actually be really useful. When you're doing something like, when we would play in like CTFs, when you go in person, they usually give you like one network cable, and that's how you connect into their network. And they'll say, hey, you need to be this IP address, this network setup, right? IP address, subnet mask, gateway. But if you have a team of like 8 or 10 people, not everyone can directly connect. So you need either one machine that acts as the router for your local team. So you have everyone else connected to a switch that's connected to one machine that has 2 network connections. And then you set up the routing table to say, hey, if you see a packet this way, send it this way, otherwise send it this way. And you can do that, all that. You can also, there's a whole field that we're not getting into of dynamically creating routing tables. And this is what, if you've never manually entered your IP address and net mask and everything, that's because everything happens dynamically. So DHCP is the name of that protocol, or basically when you first connect to a network, you send a broadcast message that says, hey, I'm new here. Like, here's my MAC address. What IP should I use? What's the net mask? What's the gateway? And then your router will respond and say, you can have IP address this, and this is the gateway and all the settings. It automatically gets configured, and then boom, you're on the network without having to set anything up. All right. Questions about routing, getting packets around? Yeah.
Just out of curiosity, what's the equivalent of like the 192.168 and for IPv6 address?
I have absolutely no idea. That was a great question. I haven't studied IPv6 a lot, so I don't know those details, but I know that there is one. I think it's maybe all zeros, but I don't know. And there's like a huge range, if I believe, like everything in IPv6 is like a huge range. So I'm sure there's like a 2 to the 64 local addresses available, those kinds of things. Yeah, I think it's all zeros actually, but I don't know. Good question. Any other questions? All right. Cool. So now that we've learned on our diagram, right, we've learned how the IP, so now we can go back to this. We didn't really study the physical layer, that's fine. We can ignore that for now. But we studied the link layer. So we looked at how packets get sent on a local network. We looked at ARP, right? How IP addresses get translated to MAC addresses. We looked at the IP layer, how packets work on the local network, also remote networks. We looked a little bit at ICMP, these messages that can get sent at the IP layer. But to be perfectly honest, it doesn't actually do much. We need other things on top of this in order to actually send real data and communicate with people. And so that's when we'll start to look at now UDP and TCP, and we'll start with UDP. So this is a way that we can actually get data to our applications. So I say almost all because networking is weird and there's always exceptions, but almost all the communication that will happen over a network will happen over TCP or UDP packets. And we'll start with UDP because it's simpler now. So UDP basically provides nothing on top of IP. It provides one important thing that we'll talk about in a second, but it provides a connectionless, unreliable, best effort datagram delivery service where delivery integrity, non-duplication, ordering, and bandwidth is not guaranteed. So it provides nothing, right? These were essentially the exact same guarantees that we had on the IP layer. And so it provides almost nothing additional. Why is that useful? It's fast, yeah, really fast. Like as we'll see, there's at least a 3 packet round trip time. So a packet has to go from you to Google and then back from Google to you and then from you to Google in order to actually start to make that request. And so you have to send 3 packets to even start communicating in TCP. In UDP, you just send a request and get a response. Send a request, get a response. Of course, you have the problem of if I send a request and never get the response, what does that mean? Does it mean the system is down? Does it mean the system doesn't want to talk to me? Does it mean that my network cable is cut? Who knows? It could be any of those things. But it does introduce one important thing, and this is, when you think about it, so we have multiple different applications, right, that are all running on one system. We have a web server, a DNS, well, I'll go with the UDP ones. We have a DNS server, we have an NFS server on one system. If I'm just sending IP packets to a system, how does it know which application those are destined to? Right, fundamentally it doesn't. There's nothing that says, hey, this packet is meant for DNS or NFS. You'd actually had some way inside the IP data to differentiate, but then what if other people don't want to use that? And anyways, it gets very confusing. So very similar, it'd be similar if anybody lived in an apartment building, apartment complex. Yeah, when you give your address to people, do they send you something just to the address of the apartment building? Why not? Yeah, there's multiple apartments. We don't know exactly who inside this building this information is destined to. So it's a similar thing that we need here. So we, the transport layer, so TCP and UDP introduced this port abstraction that basically literally acts like an apartment number. It's just a number, 16 bits. So what, 65,000 roughly, maximum. And it basically means that we can address a message to different application destinations on a host. So if we send a UDP message to port 53, then whatever's listening for messages from port 53 on UDP will get that message. And that by standard is the, I believe it's the DNS port. Oftentimes, I think as we saw, I'm fairly certain when we did the TCP dump, however long ago that was, With Zoom running, I'm fairly certain Zoom audio and video uses UDP because it doesn't really care if it drops packets. Cool. And so now we can look at that. So really, all UDP adds over TCP is this notion of a port. And so it's very lightweight. This is the other nice thing. There is a source port. Oops. Yes, so the question in Zoom is for the port abstraction. I said it's like an apartment number. So the network is like the apartment complex. So we just say for apartment 30 and apartment 30 knows how to respond. Yes. So when you're writing an application, you tell the operating system, hey, I would like to receive any packets, UDP packets on port 30. And the operating system would go, great, whenever I see a UDP packet. So it may say, hey, somebody's already listening there, so go away, you can't listen. Because you can only have one application that receives that data. So yes, so then the operating system, whenever it gets a UDP packet destined for port 30, it looks up, is anybody listening? Great, let me send that to the application. And that data goes to the application, then it processes it, does whatever it needs to do, maybe sends stuff in reply, and then goes back to listening for new stuff. And so the two main components of the UDP message are the source port and the destination port. So 2 bytes, 16 bits, a message length and a checksum, and then the data. So almost nothing, like very little on top of the other layers. And then the data. So this finally is application data. And as we've seen, right, so networking is just onions. So we have the UDP data that we actually want to send to the application. So this is the data that the application gets. We add that UDP header that just specifies source port and destination port. And then that is encapsulated inside the IP data, which adds its own IP header. And at every step along the way, that is then encapsulated inside frame data, which adds its frame header. So at each hop along the way, this frame header gets ripped off and created again, ripped off and created again. The IP header, the TTL changes, but the rest of the packet stays exactly the same. Cool. And that's it. So there's really nothing fancy on top of this. It's literally just ports. And so since we don't need to study how this works, because we literally, everything we just saw about how an IP packet works with indirect delivery is exactly the same thing a UDP packet works. It just gets sent along. The other side decides to respond. And so we talked about IP spoofing, right?
I think so. I just watched the video this morning.
Okay. Yes, we definitely did, but I'm confused. Okay, because okay. So to rewind a little bit, because UDP spoofing relies on this. So we saw when we looked at IP direct delivery that we can completely control the source and destination IP of a packet, right? We can just specify, we can send a packet on the local network and we control the IP header, which means we can control the source IP and the destination IP. And we can make that packet go anywhere we want. When they get it, they have no idea that it came from somebody else and not us. And we talked about how you could use this to abuse trust relationships inside of a network. And the same thing, now that we just refreshed ourselves of that, the same thing applies on UDP spoofing. So because it uses IP underneath, it has all the same weaknesses of IP. So as an attacker, if there's a trust relationship between a client and a server based on IP address, where the server says, hey, this IP address doesn't need to log in or do any type of authentication, or another way to phrase that would be it authenticates based on its IP address. Well, we as the attacker can simply create a spoofed UDP request to the server. So we can change that packet's IP address to pretend to come from the client. Yeah, so it's the equivalent of sending mail in somebody else's name, right? The post office doesn't authenticate that you actually wrote that name, that it's actually coming from you, or that the return address is the same, right? I think there's probably laws against that, so please don't do that. To try out don't pen test the postal system, please. Now, when the server gets this, right? So we know exactly how this packet gets from us to the server. When the server responds, where's that packet gonna go? Loud. Yeah, to the client. How do you know?
Because it doesn't know, like we spoofed that we were the client, but the server is just sending the answers to the request back to the client.
Yeah, so the server, exactly. So the server uses what's in the packet, right? So it looks at the packet and it says, who is this? What IP address is sending me this? Oh, it's my trusted client IP. Great. That means I'll allow them to do this and I'll send the reply back to that IP address, which is the trusted client. So so the question is, can we send this spoofed UDP packet from wherever we want? Yeah, there's not there. Some networks will do, I think it's egress filtering is what they call it. So they will drop packets that are getting sent from their network that have IP address sources that are not from their own network, but many networks don't. So you could fully send this packet from wherever you want, right? We saw how indirect delivery works. It'll just go out because remember, indirect delivery, what decides where that packet goes? Only one thing, the destination IP address. Nobody ever looks or cares about the source IP address, right? It's just about the destination because it makes sense, right? Because they know, hey, when the packet goes back, if there's a reply, then it will now be the destination. And so will be the only thing we care about. So I can be in any network. I can send this packet out. It will make its way several hops to the server. And then when the server replies, it will go to the trusted client. Will I ever, as an attacker, see that reply? You're shaking your head no. Why? Yeah, because the destination is to the client. So what are the only systems that will see that reply packet? What was that? Yes, the hops, right? Every hop between the server to the trusted client can potentially see that packet. So every switch, every router, every gateway that is going through is an opportunity for an attacker to observe that response. What if we're in the same local network as the trusted client? They may or may not, depending on how the network is configured. Can we as an attacker get to see that packet? Yes, how? Close. We can use an attack we've already studied. Yeah, ARP spoofing, right? We can actually, inside this trusted client system, we can ARP spoof and use a ARP poisoning attack to pretend to be the gateway for that trusted client. So the trusted client actually sends us all the packets they want to send out, which go through us to the server, and that allows us to get that reply back because the replies from the gateway will go through us to their system. So the way to think about, in general, these kinds of spoofing attacks against a target that's not in your local network is you will never see the reply unless you're in the local network of any of the hops here, and then you can do some ARP stuff to see it. Cool. Okay, so UDP spoofing means we're trying to spoof the source IP address. UDP hijacking is a slight variation. This is when the client makes a request. Like the client is asking the DNS server, hey, what's the IP address of google.com? Might that be something you as an attacker would want to influence? Why? What would you do? Or you just spent like 2 weeks thinking like attackers? Yeah, so if I change the IP address of google.com to be my IP address of the attacker's machine, they will come to me, their browser will say google.com. I will show them a web page that looks like Google. They'll click to log in. I will show them a web page that looks like Google login. They will type in their Google username and password. They'll hit enter, and I will steal that as an attacker and stolen their username and password. Now, luckily, there's other things that make this not as easy. So HTTPS cryptographic is a way to cryptographically guarantee that I am actually talking to google.com. So that is precisely to prevent this DNS hijacking attack. So DNS is a UDP mechanism. So when a client makes a, this is the other reason why being on a unsecured Wi-Fi network is incredibly dangerous, because attackers can monitor that network, see all the UDP or DNS requests, and can respond and trick you to visiting other things than you're thinking of. So anything that's done over HTTP, they could do that too. And so the best way is if the attacker also can get a copy of that request, then they can respond correctly and hopefully faster than the server. So the client gets the first one, says, great, this is a response to my query, updates everything. Can the client know that that packet came from the attacker versus the server? Why not? Yeah, the packet doesn't have, what all the packet has is source IP, destination IP, and source port and destination port. So as long as those values are all what it expects when it gets the reply, it has no idea of knowing that there's a difference there. Awesome. Okay, and then, ooh, we're doing great on time. Okay. One super important thing. So we talked about breaking into a bank, right? No? We talked about breaking in a house, but not a bank? All right. This will take 2 seconds. Okay, has anyone ever watched any crime movies? What's the first part of any crime movie when they're going to break into a bank? What's the process like? What's the first step? Yeah, first one is assembling the crew, right? Okay, after that, you got the crew. What's the step 2? Recon. You do reconnaissance on the bank. You figure out exactly when the guard shifts are, who the people are that work, what their schedules are like, everything that you possibly can about that bank. You go to the county records office to get the building plans for the bank, right? That's how they always get like the schematics and everything. You go to the people that installed the ventilation system. So maybe you can map out that thing and steal records from there. Anyways, you get all the data that you possibly can about a system. The exact same process, I guess, except for assembling the crew, happens when you're doing penetration testing of a system. So oftentimes you'd want to know, hey, for that system, what applications are running that are listening on the network, right? The other way we think about it is what applications are running on what ports of that system. Kind of like we just talked about. Is it a DNS server? Is it an NFS share? Because what I can do, oftentimes they will tell me, hey, the DNS server is bind version 1.1. And I can then go look and see, is that vulnerable to any known vulnerabilities? Can I just throw something known at it and use that to then get onto that system, scan the network from there, see what other targets I could find, and that's how you propagate through a network. So one of the key things we want to know is what services and applications are running on a system. So that's what we use a port scan for. So we determine what UDP services are available. And this is actually an interesting kind of, so it seems like kind of a weird thing, but it's a very interesting, almost like a challenge of how do you do this, right? Because you're sending one packet and you want to determine, is there something listening on that or not? So some systems will be very nice and they'll send you a message back saying port unreachable. So you try out each port. How many ports are there? 65,535, something like that. There's a lot of ports, but that's not that many. You can do that fairly easily. If we get back a port unreachable message, then we assume that nothing is there. But if they send us a response back, there actually may be a limit on how many messages they will send back. So there's all kinds of settings. Anyways, a fun tool that we'll use for these kinds of things is called nmap. So the N there stands for network map. So the -U option says you do a UDP sport scan of IP address 192.168.1.10, and it will scan that. It will say by default, it won't scan all the hosts. It'll only scan 1,445. And then it will show you, hey, these are the port numbers that I see up. The service name, again, nothing guarantees that a certain application or service is running on a given port. It is just convention, because we need to be able to, when I make a DNS request to a system, I need to know what port to use. So by convention, port 53 is the DNS port. Just like port 137 is NetBIOS NS and port 138 is NetBIOS DGM. It's cool. So, wow, we did a lot today. So we will start on TCP on Thursday.
I just remember the virus that you like, UDP, the basic crash.
Which one?
Slammer.
Yeah, and Code Red was another one.
What was that?
I don't know. I think